with Ethan Morris, episode number 512. Welcome to the Smart Buildings Academy podcast. In today's episode, we'll be looking at air handler sequences for operating rooms and clean rooms and how we can understand those sequences a little bit better. All the information covered in this episode can be found on our website at podcast.smartbuildingsacademy.com/512. Again, that's podcast.smartbuildingsacademy.com/512. To start this episode off, let's look at the objectives we have for today's episode. The first objective here is to understand the role of air handlers in operating rooms and clean room performance. Then we'll learn some common sequence strategies and why they matter. Then we'll explore some compliance requirements that deal with ASHRAE, USP, and the ISO standards. And then we'll identify some optimization opportunities for efficiency and safety. Fundamentals of critical AHUs, or air handling units. The purpose of an air handler in an operating room or clean room environments would be that they supply clean, filtered, conditioned air at the correct pressure and temperature. They maintain pressurization, which is positive for operating rooms and negative for some clean rooms depending on their use. And it also ensures the proper amount of air changes per hour, or ACHs. The key design differences between a operating room or clean room air handler and a standard air handler is that in a operating room or clean room air handler, you would find a redundant fan or a dual fan configuration. This would be for if you had a fan motor fail during operating hours. This would be a fail-safe for a secondary fan to come on so that you're still providing air to the space if you do have a failure of some kind. The next thing we see here is the HEPA filtration stages. You got to have HEPA filters in these air handlers because it needs to catch more particulates. Remember, these clean rooms, we're trying to keep out any infections and particles, things that can get into a clean room or an operating room and hurt either a patient or whatever they're working on in those clean rooms. And then the last thing we see here for this is tight control tolerances for temperature and humidity. If it's a typical building like a college or a college or even a dorm room or an apartment building, most HVAC equipment is just going to have like a simple 2-3 degree deadband. We may see something in an operating room or a clean room that has like a 0.5 degree deadband, something that doesn't, there's not a lot of fluctuation allowed in the temperature or the humidity in those rooms. So we'll see tighter control tolerances for temperature and humidity in these air handlers, aside from standard air handlers. So why is it important for us to know the sequences of operation for these? Sequences of operation are not just on and off. They define how the systems behave under normal, occupied, unoccupied, and failure conditions. So, it's not just as simple as turning the unit on or off. There's a lot of ins and outs on these sequences, and we need to make sure that we can read and understand those and understand how the equipment is supposed to run for our application. Next thing here is typical sequencing that we would find in a air handler for a operating room or a clean room. So the first thing here is the startup or initialization sequence. First thing we do here is the pre-start checks. Not we in particular, but our programming, our front end, the BAS system itself. It'll do its pre-start checks. So it's going to verify that dampers are closed, that safeties are either clear or okay. If all those are good, then we start the fan with, typically nowadays we use variable frequency drives to speed up and slow down our fans. So in this instance, we have a VFD driven supply fan. So we've gotten through our pre-check with the dampers and the safeties. Now we're starting our fan, ramping it up slowly from 0 hertz all the way up to whatever the room air pressure needs to be. It will ramp our fan up to that speed. Then after the fan comes on, we get a delay before the chill water or the steam valves, hot water valves, whatever you may have in your unit, before they start to open or modulate to handle our room conditions. So after the startup and initialization sequence, we'll look into our filter and airflow control. So once we get to this stage, we have our multi-stage filtration. So we've got a MERV pre-filter and then a HEPA final filter. So we need to check and make sure that our filters are clear, usually done with a differential air pressure switch, so we can tell if there's a good enough differential of air moving through our filter to tell if it's clean or not. The second thing here is monitoring that filter differential pressure, which is what I was saying with checking our filters if they're clean or not. And then we go to airflow tracking to maintain our specified air changes per hour. So these sequences are going to track our airflow. We'll have an airflow sensor either on the air handler or somewhere in the duct. And we'll track that airflow to make sure we're getting the right amount of ACHs per hour in our sequence. So then that's filtration and airflow control. So then once we move on from those, we get into our temperature and humidity control. This is the big one for our operating rooms and our clean rooms. So remember in the last slide, we talked about there being tighter tolerances on our temperature and humidity controls. This right here is stating that. It's stating that tight deadband, for space temperature. This could be plus or minus 1 degree or less. So like I said, typical classroom, commercial style building, I've seen 2 degree, 3 degree deadbands set for those. But in this instance with an operating room or a clean room, we may need that to be a half a degree or a degree. So yeah, much tighter on the tolerances there for our deadbands. So that's our temperature, our space temperature control. Next thing here is our humidity control. This often requires both humidification and dehumidification. So that's why we were stating the steam valves up at the top there with the startup and initialization. So if we're humidifying a space, typically that's done with low pressure steam. So in these operating rooms and clean rooms, we will need some form of steam, low pressure steam, to humidify the space if our humidity drops below what we need it to be. And then we also need to be able to dehumidify this air if our relative humidity in the room starts to get close to our top end set point. So typically for this, probably somewhere between 40 to 60% humidity. So remember, it's very, very important we have humidity control with this so we can humidify the room. And we also have dehumidification control so that we can dehumidify the space as well. Then the last thing here for temperature and humidity is the reheat sequences for precise control. So typically with these, we're going to be sending out a constant volume of air, usually to like a VAV box. And we're going to be sending a constant volume of air from our air handler, and that could be 55 degrees, 50 degrees, whatever it's required in that space. And then we just use a reheat to reheat the air before it goes into the space. That way we don't overcool the room. So that reheat sequence also needs to be gone through, make sure it's tight, make sure it works well so that you're not cooling the room off too much. Okay, so that's the first part of our typical sequencing. We move on here to a continuation of that. So after we get through the temperature and humidity control, we move on to our pressurization control. So with pressurization control, our operating rooms typically need to be running in a positive pressure relative to their adjacent spaces. Clean rooms can be positive or negative depending on their application. An example here would be sterile compounding versus hazardous drugs. Hazardous drugs, you would want that to be a low pressure. You don't want any of those particles leaving the room if somebody opens a door. So that space would need to be a low pressure area. If we were doing sterile compounding, that would be vice versa of this. We would need high pressure for this. Then we've got at the bottom here the role of supply versus exhaust airflow tracking. So a supply, if you think about it, a supply box or supply fan would be pushing air into a space, and an exhaust fan would be pulling air from the space. So if that's taking place when we're talking about pressurization and pressurizing a space, we need to remember that our supply fan and our exhaust fan need to be somewhat close so that we're removing and supplying the same amount of air or close to. Now, obviously, if you're in a like this example here, operating rooms typically run in a positive pressure, so we would need more supply air than we would need exhaust air. And then on the flip side of that, with clean rooms, if they, let's say in this instance, a clean room would need a a negative pressure in the room. Then we would definitely draw more air out with the exhaust fan than we would supply with the supply fan. So it's kind of a little give and a take there with pressurizing a room, but it's very important that you have airflow measuring stations or airflow sensors on all of these ductwork, all the duct that goes in, supply duct, exhaust duct, so that you can make sure that you're tracking how much CFM of air you are supplying into the room and exhausting from the room. So that's our pressurization control sequence. Again, this can change. Again, it's kind of depending on the application for the clean room. Again, ORs typically are positive pressure because we don't want to suck anything into the room in case they have a patient that they are operating on. Again, infection and contaminants are a huge thing in operating rooms, so positive pressure is what's usually needed in those. So that's our pressurization control. Next thing we'll move on to here is the alarms and monitoring section. So critical alarms here for alarms and monitoring would be a loss of pressure differential. So if we had a airflow sensor that went bad all of a sudden and we weren't getting a pressure reading off of it anymore, we would need an alarm for that. The next one here is an out of range humidity. So again, if our humidity drops below the minimum that it can, or if it rises above the top end of our scale that we set, then we need to have an alarm set up so that, let's say we have a 55% humidity set point in an operating room, but the humidity gets to 58%. When it gets up to 58%, we need our BAS to send us an alarm so we know that there's an issue. Same thing with our pressure control, pressure differential control as well. If it loses its air pressure reading, or if it gets outside of its humidity range, then we need to send an alarm. And then the third example here would be fan failure. So this ties back in with the redundant fan motor in some of these units. So we would have the one fan motor drop out, BAS sends us an alarm, and then if we have our sequences right, tight enough, programmed well enough, then that fan will fail, but we should have our secondary redundant fan come on in its place, so we're still supplying air to the space. So those are our critical alarms we should put in place with our BAS so that we're notified when things go wrong. And then at the bottom there with our alarms and monitoring, we've got integration into BAS dashboards for visibility. This is just saying that if you guys have a front end, just throw these alarms on the main page so that they're easily seen if somebody comes up to it and logs into the site. So that is our typical sequencing for a air handler in a operating room or a clean room. Next here, we'll look at some special considerations. So for operating rooms, a couple special considerations for those would be laminar flow diffusers above the surgical tables. So you don't want the air blowing directly down on the table. So this would push the air kind of out towards the drop ceiling or whatever ceiling you may have in the room. Next thing here is requirement for continuous monitoring of temperature, humidity, and pressure. Remember, this is an operating room. So a big thing for here in these spaces is keeping out any kind of infections or contaminations. Remember, they may have someone in there on a table that they're operating on and can't have any kind of particulates or anything getting into that room. So positive pressure is huge, and temperature and humidity control are really, really big things with operating rooms. Then we have redundant strategies down here at the bottom for operating rooms. This again just goes back to our redundant fan in the air handler. So if we have a failure, we have a backup on standby just in case something goes wrong. So make sure you have redundancies in place just in case something does happen. It's mechanical. Things that are mechanical are going to break eventually. It's just how it goes. So make sure you have redundant strategies in your sequences for some of these as well. So those are our special considerations for operating rooms. Next thing we'll look at are our clean room special considerations. So the first thing here is the classification levels. This ties back with the ISO 5 through 8 specifications. Then below that, we have how tighter classifications drive sequence complexity. So the tighter the classifications on our sequence, they get a little bit more complex. So it takes a little bit more time to set those up and get them right. So just be aware of those things. And then the last part here for clean rooms is the role of gowning rooms and airlocks in maintaining pressure cascades. So you think about this, if somebody goes into a gowning room, they open the front door to go into it, there may be another door after that to get into the operating room. So we have to think about people going in and out of these rooms and how that's going to affect the pressure, temperature, and humidity in our clean room. So we have to set all these things in our sequences, and there's a lot of things we have to take account of, especially when we're talking about these. But like I said, these are all special considerations. So just make note of these when you guys are setting up your air handlers or working on them or troubleshooting. Look through the sequences and see if they have these things in place. Next here, we're going to look at some technician and operator insights. So for technicians, this is a BAS focus up here at the top. The first thing here is to ensure airflow sensors, differential pressure transmitters, and humidity sensors are all calibrated. Okay, so if we put sensors in these rooms and they're off 5% on humidity, if it's reading 250 CFMs above what it's supposed to, or if the temperature sensors aren't reading right, if they're a couple degrees off, it's going to throw things way out of whack, and your rooms are never going to be within the rules that they've been set before them. So make sure that you're ensuring these sensors and devices are all calibrated. And sometimes that may mean changing those sensors out if you can't calibrate them correctly. So just keep that in mind. The next thing is to validate your control loops. Many issues arise from poorly tuned PID loops or poorly formed programs, functional programs. So make sure when you're going through and setting all this up that you're running through your control loops, enabling them, and even simulating them if you can somehow, just to make sure that they're operating how you have them set. So validate your control loops. Then last thing here is to test failover and alarm sequences regularly, just to make sure that they work. Sometimes things can change in our front ends. Points can change, devices can change, things can stop working. So you need to make sure that you go through and you're checking these. Sometimes you can make it to where you can trigger the alarm manually if you go do something in the room. You may be able to get these alarms to trigger manually just to test them and see if they're working right. So those are 3 insights for technicians. The next thing here is going to be insights for operators. This has a more of a facility style focus. So operators, when you're walking through your buildings, working on things, watch for subtle drifts in humidity or pressurization. This is early warning of filter loading or control drift. So obviously if you're starting to feel some changes in humidity or pressurization, so if it's harder to open a door or if a door won't shut all the way, obviously that's a pressurization issue. If you can't shut a door, the room's overpressurized. If you can't open the door, then there's negative pressure in the room, so it's sucking the door in. So these could all be early warning signs of filters needing changed, or maybe a PID loop in your control stop working. Maybe the PID loop got off kilter somehow. So maybe you need to go back through and work on that a little bit. So watch for these subtle drifts. They could be early warning signs of a problem. Next thing here for operators is don't override the sequences. These are engineered for safety and compliance. So let's say you have a chill water actuator on the air handler that it opened and then it failed. So we needed chill water to go through the coil so we could cool off our supply air. The chill water valve opened, but then once it opened, it never closed back down. So we overcooled the air and our room is freezing cold. Typically somebody could go in and override the point on the front end to closed, and it would just close the chill water valve until you opened it again or re-enabled the point. But what this is saying is don't override any of the sequences or the devices, because if you do, let's say for this instance, if you were to override that chill water valve to closed, by the time maybe a week later, it could be way hotter in that room and nobody knows why. And then you go back and think, oh, it's because I overrid that point last week and left the valve closed. But we fixed the valve. It's just not working. That could be a big problem in an operating room or a clean room. Obviously, tight temperature and humidity tolerances. So if you override something and it's not operating how it's supposed to per the sequence, That can cause major issues, so just be aware of that and do not override sequences or devices. The next thing here is to ensure maintenance schedules for filters, humidifiers, and sensors are followed. This goes back to our preventative maintenance. If you're in a hospital setting like this, where you have an operating room or a clean room, your preventative maintenance schedule is probably going to be a little bit more hefty than what just like a college or K through 12 type of PM would be. But make sure that in your maintenance schedules you have time and tasks in there for checking the filters, checking the humidifiers, and checking any of the sensors that are tied to that air handler that are feeding those critical spaces. So those are some insights for the operators with a more facility style focus. Then down here at the bottom, we've got some common troubleshooting examples for these rooms. So the first troubleshooting example here would be the room won't stay at a positive pressure. So for me, the first couple things I would check is the exhaust supply balance. So check the CFM we're getting out of the supply and pulling back from the exhaust. Make sure that those are within the bounds what they should be. The next thing I would check is door seals. These doors should have some seals on them, so when they shut, you're not getting any air filtration through the door. Make sure that those door seals are good. If the seals have come off or if they've been broken or rubbed down over time, they may need to be replaced. Then the last one here is filter loading. Big thing here is just always check your filters, guys. Filters are going to be huge. Remember, HVAC is big on airflow, and if our filters are clogged up, if they're filthy, we're not going to get very good airflow through our air handler, and that's going to cause our rooms to go way out of whack. So make sure you're checking all these things when you're doing your troubleshooting. It'll help you out a bunch. Next example here is the humidity being out of range. What I would check is make sure that the humidifier scale buildup or cooling, or I'm sorry, excuse me. I'm going to check and make sure there's no scale buildup on the humidifier. So calcium buildup, anything like that might need cleaned if we're not humidifying properly. Then I would check our cooling coil bypass to see if our bypass is closed, if we're pushing chilled water into the, or I'm sorry, excuse me, opposite of that. I would check to see if our bypass is open. We need to make sure our bypass is closed so that we can pass chilled water through the coil effectively. Then the last thing here for our troubleshooting examples would be our temperature swings. If we're having major temperature swings in our rooms, we need to make sure that our reheat valve isn't hunting, so it's not just opening, closing, modulating back and forth and back and forth. And then make sure that we don't have a poorly tuned PID loop. So make sure that our PID loops are tuned well. Make sure they're operating right. Okay. So those are just some common troubleshooting examples I would run through with some common problems we may see. All right, then a little case study example I have here, just so you guys could see how I would run through if we have an issue. So our problem here is excessive energy use in an operating room air handler unit. So the solution I would do if I found that would be to implement some kind of occupancy-based sequence so that the unit's only running if it sees movement in the room or if it's part of an occupancy schedule. The result of that could be maintain compliance with our scheduling, and it cut our energy usage by 20%, which saves us cost as well. So lessons learned from this: I would always set up alarms and trends to monitor the system easier and faster. If we had trends and alarms set up for this, we could have seen the excessive energy use earlier on and maybe saved a little bit more money a little bit sooner. So in summary for today's podcast, we learned that air handlers are mission critical in operating rooms and clean rooms, and that their sequences are balanced for safety, compliance, and efficiency. We learned that standards provide the framework, but optimization on our end is what adds the value. And then last point here is that proper monitoring and alarms are non-negotiable. If we use these things, it can help us get things fixed a lot faster, and we can monitor things a little bit easier too. So thank you for listening to the Smart Buildings Academy podcast. We hope you learned something from this episode. If you found this episode valuable, please leave us a 5-star review on Apple Podcasts or Spotify. If you're watching this on YouTube, please like, comment, and subscribe. As always, this will be available on our website at podcast.smartbuildingsacademy.com/512. Thanks. I appreciate your time, and I hope you have a great day.